Good evening, and thank you for joining another one of Casio's mathematics webinars. Tonight we're looking forward to hearing from Nancy Foote, one of Casio's Teacher Advisory Council members from Gilbert, Arizona. Nancy has a broad experience ranging from time spent as an industrial chemist to teaching at both elementary and community college levels, as well as middle school. She's an excellent teacher in mathematics and science. Nancy's topic for tonight is forces and motion in math. Oh my. One quick note for those in our live audience: you have all been muted for the sake of audio quality. If you have any questions, you can type them into the question panel on the right-hand side of your computer screen, and I will probably answer them myself, or if I need to, I'll pass them on to Nancy at the end. All right, Nancy, the microphone's all yours.
Well, thanks, Terry, and thank you, ladies and gentlemen, for giving me some of your valuable time. I know that if you're anything like me, my most valuable resource is my time, and I really appreciate you spending it with me. Today we're going to go over some very basic math and science, physics specifically, and a lot of this I'm going to take you through as if you were my student. I'm a veteran teacher. This is my 26th year in education. And I've taught physics a lot at many different levels, and I found that one of the most important things to me, at least, is that kids have to have a good, strong foundation in math to be successful in physics. I always tell them math is the language of science, and it is. And so today, let's get a little bilingual and let's learn how to talk science as well as talk math. So the first topic we're going to cover is scientific notation. And scientific notation, as you all know, is simply a way to express really, really big numbers or really, really small numbers. But rather than just give kids worksheets, which they hate, I like to give them questions that deal with stuff that's reality. So why don't we spend a minute and work out our first problem? How long would it take to drive to the sun at 70 miles per hour if it's 92,960,000 miles from the sun to the earth? Now, kids tend to shy away from problems like that because it's big and it's ugly and it's not very user-friendly. But when you turn that into scientific notation, it becomes a very easy problem. On my next screen, I'm going to show you more specific details, but why don't you take a minute and work through that and see what you come up with. I'm going to give you about 30 seconds. We'll go really fast because we have calculators to use today. As you probably already know, the equation is time is equal to distance divided by speed. So we take our distance of 92 million miles, 93 million miles, and divide it by 70, and we come up with over 1 million hours. Well, that number is a huge number, and kids have a hard time wrapping their heads around it. So let's talk about how many days that would be. If there's 24 hours in a day, that ends up being about 55,000 days, which is still a number that kids may or may not be able to figure out. So let's figure out how many years that is. And if we ignore leap year, it ends up being 151 years. Now that's something that they can understand. So if we were going to take our cars and drive to the sun, obviously we couldn't do it, but if we could, it would take us 151 years going at 70 miles per hour. Again, we need to take those very big numbers and make them reasonable, make them things that kids can understand, and that they have a, I call it a spidey sense about, that they have a good way of figuring out exactly what we mean by 93 million miles. So let's do another million problem. And this is one of my favorites, and I'd like the audience to, if you can, I don't know if you can or not, in the question box, just give me your estimate. If you started counting on January 1st at midnight, how long, what day would it be when your heart beat the 1 millionth time? So 1 is going to be January 1st at midnight. What day would it be? So just give me a guess what you think it is. Put it in the question box, and just let's see what we come up with what kind of predictions people have. And just use your spidey sense. Don't try to be mathematically accurate. Just think, 1 million heartbeats, how long would that take? Okay, so I see we have a couple of predictions. Let's actually do some calculations. If we started counting on January 1st at midnight and it was going to count 1,000,000 times, we have to figure out how long that would be. What do we want to do? Well, first of all, we have to find out how many times our heart beats in a minute. And most people, it's right around 70. If you're more athletic, it's less. If you're like exercising or that kind of thing, your heart rate might be elevated. Or if you're like me, you're just a little bit nervous, my heart rate is probably elevated. But let's say 70 beats a minute. So at 70 beats a minute, it would take 14,286 minutes to beat 1,000,000 times. That's a long time, right? Well, maybe. So let's take that 14,286 minutes and turn it into hours. If I did my math correctly, it ended up being 238 hours. But here's the most surprising part. When we turn that into days, it's less than 10 days. So if I started counting on January 1st at midnight, my heart would beat its 1,000,000th time somewhere probably right around January 10th. Now I'm sure, looking at some of the predictions, people guessed way later in the year than that. Again, talk to your students about that. Let's give them an opportunity to kind of use their spidey sense and see what makes sense to them. Last question, sound travels at 771 miles per hour in dry 70-degree heat. That's really important, the temperature and stuff. Maybe not for non-scientists, but for scientists it's critical. You can ask kids how long would it take for a message to get from Phoenix to New York City, how long would it take for a message to go around the world, how long would it take to have a conversation with someone, you know, in their favorite city that's not where they live. But let them do a little research. Let them figure out how far it is. In my school, the kids have iPads, so they have access to the internet. They can very easily go on, do a little research, figure out what's going on, and then come back and apply it. The other day we had a question about a plane and a tailwind, and the kids didn't know what a tailwind was. And a lot of them just went online and Googled it and found out what a tailwind was as opposed to a headwind. So it was a learning opportunity for them. For this question I have here, 771 miles to New York, it's going to take about 3.12 hours, which tells you exactly how amazing technology is. I am sitting in my home in Phoenix, and this is being broadcast almost instantaneously throughout the world, which is just so mind-boggling to me. It just amazes me. So I started thinking a little bit about all kinds of stuff and about big numbers and where are we going to see big numbers. And the one place that I noticed is they've been having a few little problems with like Google, and it went down for a couple minutes not too long ago, and Twitter had a problem, and so I started thinking those are really big numbers, and I did some research and I came across this graph, which was just fascinating to me, and I think that your students will find it fascinating too. So what this represents is the brand value, the value of the brand, and it's too complicated for me to understand exactly how they put it together. But it used to be that Coca-Cola was always the brand. The brand to beat was always Coca-Cola, and it's the red line here, and it's fairly linear. Microsoft is the blue line, again, also fairly linear. But then look at this. This amazes me. Apple starts out, goes down a little bit, exponential growth in the last few years. And Google, which came on the scene in 2005, has just skyrocketed. So here's some nice big numbers for your kids to work with and a beautiful graph. You can ask them how much more is Apple's value than Coke's value? What percentage is that? What percent decrease did they have over the, or increase did they have over the last 2 years? How about Microsoft? It looks like they're going down from, you know, the late 90s. What's their percent decrease? When kids take standardized tests, they need to be able to interpret graphs. This is a beautiful graph, and this same website down here, you can create your own infographics. So if you haven't done those with your students, you may want to consider doing it. Use those big numbers, those scientific numbers, and go ahead and see what they came up with. So now we're going to talk about metric conversion, and I love the metric system. I really cannot stand the fact that the United States does not use the metric system. The big thing is it's easy. It's based on 10. I mean, if you think about our system, it's based on a little bit of everything. What's an inch broken into? If you look at a ruler, an inch is broken into usually eighths or sixteenths, right? And what's a foot broken into? 12 inches. And what's a yard broken into? Either 3 feet or 36 inches, depending on how you look at it. Nothing nice, nothing consistent. No wonder it's so hard to learn. We're one of only 3 countries in the world that actually don't use the metric system. The metric system is based on 10, but for a lot of my students, the biggest selling point is that it does not involve fractions. It can, yes, you can say 1/10 is 1 over 10, but it's easier for me at least to say it's 0.1. It's based on a series of prefixes and root words, which we're going to talk about in just 1 minute really quickly, and it uses a mnemonic device, the way that I remember it, and that's why my little king and my chocolate milk is sitting there. So prefixes, again, I'm not going to teach you something you already know. I'm not going to read you a PowerPoint. There's your prefixes for the metric system. I know it said it doesn't include any fractions. Sometimes kids prefer to see it this way than this way. Decimals can be scary to them. I don't know why, but fractions are even worse. So here's the mnemonic. It's called, I do a thing called the metric hop. The mnemonic device is King Henry died unexpectedly drinking chocolate milk. And the letter for each one of those stands for one of the metric prefixes in order. King Henry died unexpectedly drinking chocolate milk. Unexpectedly is where you're going to have your root word or your base word, something like that. And again, there you have it. So that's the mnemonic device. Let me show you how to use it. So I call this at the hop, and I'm going to show you a little video I made this afternoon in school.
Okay, so let's go through step by step how I would teach my students to answer one of these questions. How many millimeters are in 57 centimeters? So we know 57 centimeters, we're trying to figure out millimeters. And I take them through a series of steps on how to solve these. So there's our 57 centimeters. First of all, I have them write the 5-7 and show the decimal. If it's invisible, we'll show it. Then I have them add extra zeros. Use your slider and count the jumps. So here's what it looks like. Begin with what you know, 57 centimeters. If I show the decimal, it's still 57. If I add zeros before, it's still 57. And if I add zeros after, it's 57. Now eventually they get cognizant enough to know that you don't have to add zeros both at the beginning and at the end. When I first start teaching them this, I do teach them both at the beginning and at the end. And here's the slider. We're going to go from centimeters to millimeters, centimeters to millimeters. So I'm going to put my pointer on where I start and go 1 jump to the right. So 57, there's my decimal. There's my extra zeros at the end, my extra zeros at the beginning. If I take and go 1 jump from here over to here, 1 jump to the right, it's 570 millimeters. So here's another example. 1,492 liters is how many kilometers. Let's use our slider to find out the answer to that one. There's our slider going from meters, which would be right here under units, to kiloliters, which is right here. So we have to go 1, 2, 3 jumps to the left. 3 jumps to the left. 14.92. 3 jumps to the left becomes 0.01492.
Okay, so wasn't that exciting? I'm sure you think it is. I do a lot of videoing for my kids. My classroom is a flipped classroom, which means I don't lecture in class. All I do is I have them watch the video of my lecture at home. Lectures are usually between 5 and 8 minutes. And then we do the problems, the hard part, at school. That's when they need help most, when they're trying to figure out the problems. They don't need the help when they're trying to listen to a teacher, talk at them. So next thing is dimension analysis. And dimension analysis is, to me, one of the most important parts of physics and chemistry, because if a student can do dimension analysis, they can do just about anything, and they really don't have to memorize much. So let's take a watch. This slide is a little bit, this video is a little bit longer, but I think it'll give you the real idea about dimension analysis and how to best teach it.
Nancy, I cannot really
Yes.
hear anything while you're showing the video.
All right, let me turn it up. Is that any better?
Not for me. I don't know about other people.
So on one hand, I have $1, $1, $1,
If I turn my mixer up real loud, I can hear barely.
Okay, I don't know. It's blasting in my ears, so.
Okay.
Well, we can just skip the video. I can talk you through it. Let me go ahead and turn the volume down so that I can hear. So basically what I'm doing here is I'm saying sometimes things can have the same name, have different names, but have the same value. 5 $1 bills have exactly the same value as one $5 bill. And so that's what we do with dimension analysis. A lot of students are going to ask me, when do I multiply, when do I divide? And I always tell them, you don't worry about multiplying, dividing. You're always going to multiply by something that's equivalent to 1. I could say that one $5 bill or 5 $1 bills are the same thing. And if I put it as a fraction in both the numerator and the denominator, it is exactly equal. So it's like writing 1. Now we're going to do an example. We are saying 3 days, and we're going to convert that into how many seconds are in 3 days. So we need to have some conversion units. We have to have some things that we know about days and seconds that we can put together. So let's start with that. Again, I'm a little off balance now that I don't have my audio. So 24 hours is 1 day. We all know that. And we also know that something smaller than an hour is a minute. So I'm guessing I wrote 60 minutes is 1 hour. Something smaller than an hour is seconds. 60 seconds is 1 minute. And so what we're trying to do now is get seconds into days. And the way we do that is by making this long chain of multiplication by 1. So we always start by writing what we know. In this case, it's 3 days. And we're going to multiply it by something that's equivalent to 1. Now, let's see if I do this. Normally I put the 3 days over 1. Okay, 24 hours and 1 day mean exactly the same thing. So if I wrote it as a fraction, that'd be equal to 1. And what we all know, when you multiply something by 1, it doesn't change anything. It stays the same. 37 times 1 is still 37. 496 times 1 is still 496. So 3 days times something that's equivalent to 1 is still going to be equal to 1. Now I did put it over 1 because I want my students to remember that that 3 days is in the numerator, and we actually do have a denominator. It's 1. It's invisible, but it's there. It's important that they know that because when they cancel out the numbers, when they cancel out the words rather, they need to know whether the word days needs to go in the numerator or the denominator. And so I gave them an example and I said, if you had a problem and your answer was 12 over 30, your teacher might ask you to simplify it or cancel it or reduce it. But what is she really asking you to do? Well, she's asking you to take out any ones that you can. 12 is the same as 3 times 4, and 30 is the same as 3 times 10, and 3 over 3 is 1, so we can get rid of it. That leaves 4 over 10. If we look at that, we say, oh, guess what? I know something else. I can say 4 is 2 times 2, and 10 is 2 times 5. And now I see that I have a 2 over 2, which is 1. So when we reduce something from 12/30ths to 2/5, what we're actually doing is we're taking out equivalent fractions. We're taking out things that are equal to 1 so that it has the same identity or the same value. Likewise, if I have the word days in the numerator and days in the denominator, that's going to equal 1. So I can, as they say, cancel it out. Now I want to get rid of days, and the only thing I have to use on days is hours. The number 24 is next to hours. So when I write over here, I'm going to write 24 because that's how many hours there are. The number 1 is next to day, so I'm going to write 1. And again, days over days can be crossed out, can be canceled out because 1's in the numerator and 1's in the denominator, and that equals 1. So if I did my math right now, 3 times 24, that would give me the number of hours, but I was asked for the number of seconds. So I'm going to do the same thing again, only now I'm going to get rid of hours. Hours in the denominator, and the way I can relate hours, the thing I can relate hours to is minutes. Minutes in the numerator, 60 goes next to minute, 1 goes next to hour, and then you're going to see that I have hours over hours, and so I can cancel them out because they're equal to 1. That's the only reason I can cancel them out. A number divided by itself is 1. So now I have minutes. I want to get rid of minutes, and I want to be left with seconds. Now some people are fortunate enough that they know there's 3,600 seconds in an hour, in which case you could have done this in only one extra step. But let's pretend like you didn't. Minutes is in the numerator here, so it's going to be in the denominator here. I'm going to change minutes into seconds. And when I do that, I take 3 times 24 times 60 times 60, and then it's divided by anything in the denominator, which in this case is 1. So let's see what I came up with. $259,200 seconds in 3 days. Okay, we're going to go on. There's more on this, but we're going to go on. This slide was actually put out of order. It should have been with the metric system. It's one of my favorites. Metric system is something we've been struggling with for a very long time. So I'm going to let you take a minute and go ahead and read that and give yourself a little giggle just like I did when I saw it. And if you're anything like me, the very first thing that I did was I checked this box to make sure that it was correct, because I don't like finding things incorrect in the media. However, I should have just realized that Charles Schultz knew what he was talking about, and he was right. I don't do homework in my class, and I don't do worksheets. I do learning opportunities. So this is a learning opportunity that I might give my kids. Now, I had a really hard time figuring out how many burgers were sold by a specific restaurant chain. There's websites that say it's 400,000, it's 400 billion, 500 billion. I just thought 250 was a nice round number, and when you speak with authority, kids believe you. So have them find it out. If the hamburgers are ½ an inch thick, how tall would a stack of these hamburgers be? Well, if they're smart, they'll realize that all they have to do is divide this by 2, and they're going to get 125 billion inches. So I would ask them to tell me it in centimeters, or in millimeters, or in feet, or in miles, something like that, just to see if they really know how to do the change. Also, here's another one that you can use scientific notation together with metric system. How does the height compare to the distance to the moon? It'd be interesting to have them find out. But what I really wanted to show you, nope, yeah, that's right. There you go. So while you're listening to this little musical break, which only lasts about 30 seconds, see if you can figure out, are there 525,600 minutes in a year? See if you can figure that out. And one of the things I really like about that part of that song is they give a lot of non-standard units of measure. They said, how do you measure year? In sunsets, in cups of coffee. If you did it mathematically and you ignored leap year, you would find out that, yes, the 525,600 minutes is exactly correct, ignoring leap year. But let's talk a little bit about a calculator, because I just have to show you this really cool thing. I encourage, gosh, everyone to get this calculator for so many reasons, but here's one of my favorite things that it does. And it's unfortunate that you may not be able to hear the video. I'm going to turn it up really loud anyway. This is the Casio FX115 ES Plus, and this is the inside of the cover, which is like my little cheat sheet. I never have to remember where anything is or have any problems with using it because it's intuitive. It's icon-based. The graphers are, and once you know how to use one Casio calculator, you know how to use all of them. You don't have to learn it again and again and again. But this unit conversion piece is pretty interesting to me, and the scientific constants, huge difference to me. So let's take a quick look, and I'm gonna turn the volume all the way up and see if maybe we can hear this one better.
inches to centimeters, I'm going to hit my equal sign, and it gives me a fraction. I can set my calculator so that it's always in decimal or so that it's always in fraction. Right now it's set to be in fraction. But to convert that to a decimal, I just press this S to D key, and it changes your fraction into a decimal. So 57 inches is about 145-ish centimeters. Let's do another conversion. One of the things we frequently deal with is meters per second. So let's say 35 meters per second, and we want to change that into kilometers per hour. So again, Shift 8 gets me into the conversion. Kilometers per hour is meters per second to kilometers per hour is number 20. And there you see meters per second to kilometers per hour, so we don't have negative numbers, which is good. We don't like that in science. Press my equal sign, it's 126 kilometers per hour. You don't have to remember this. It's all written on the cover of the calculator. Let me show you what that looks like.
Okay, so hopefully you got to see that and you could hear at least a little bit of it. This is incredibly invaluable to me and to my students. I do make them go through learning how to do it without the tool because I think it's good for their brains, and I think it's good for them just to know how to do it. They're not always going to have a calculator handy, or maybe they will, but it's good for them to learn how to do it. And then I give them the tool, and I explain to them that this is going to save them so much time throughout not just middle school, but high school and even college. I mean, if you look at this calculator retails for under 15 bucks, and during back-to-school sales, you can usually get it for under 10. It even has integrals in here and all kinds of stuff. It's also got natural display fractions, so a fraction actually looks like a fraction. Imagine that. And there's not those crazy L's and 7's and backwards numbers and letters and all that stuff. So let's go ahead on and let me show you how I know for sure that a student really gets conversions. I give them nonsensical conversions that I just made up all by myself. So I talk about going to the store. I'm a farmer. I'm at the store. The only thing that I am able to do is grow apples. I have apple trees. That's all I want, but I really need to bring home some pineapples. So is there any way I can take my apples and change them into pineapples? And the kids eventually figure out, yeah, there's ways. I can go from apples to pears, pears to bananas, bananas to grapes, grapes to oranges, oranges to plums, plums to pineapples, and eventually I can get a pineapple. Of course, I start out with much easier ones. How many pears do you get from 10 apples? And we get progressively more complicated. This is a fantastic way for me to find out exactly if they understand unit conversion or not. Again, a critical component in any math or science class. Oops, sorry, I bumped my calculator. In any math or my computer or any math or science class is the metric or the conversions, the unit analysis, the being able to look at it and figure out what you need. If all you know is the units, you really don't have to memorize formulas. Students don't believe that, but it's true. Let's go on this next one. I think you'll like this next one. I hope you can hear this. This is my favorite. Vectors and scalars. I like going to the movies, mostly because I like having the movie popcorn, but we'll pretend like I like going to the movies so that I can go to the movies. And I saw this and I thought this is a teachable moment. So let's see if I can crank the volume on this. Oops, sorry, gotta go back.
Nancy, try putting your headphone microphone by your computer.
Okay. Well, it's coming out of my earpieces. I have a headphone on. Basically, what's happening, this is from the movie.
Never mind.
This is from the movie Despicable Me, and actually the kids shared this with me. They took a pretest, and one of the students said to me, "Well, I knew what a vector was," and I was stunned. I said, "How do you know what a vector is?" And she says, "Oh, it's something that has magnitude and direction." And I said, "Yeah, you're right. How did you know that?" And she said, "I saw Despicable Me." And so of course I had to go back and I had to find the clip from the movie, and I showed this to my students, and the math teacher at my school later told me that she had been talking about vectors with her kids, and she said they knew what it was. And I still say it's because of Despicable Me. So thank you, Hollywood, for helping me teach a little bit of my science. Now we're going to talk about forces. Vector, magnitude and direction, and scalar is magnitude only. Magnitude means size. That's usually the number. Okay. So we're going to talk about forces. When you ask students what a force is, they will all tell you the same thing. They will all tell you the same thing. A force is a push or a pull on an object, and it is. I usually call it, like, instead of a tug of war, a tug of forces. If and that's me actually there on the left, or Einstein, I'm not sure who. If we pulled with 200 newtons and we had kids pulling with 100 newtons, obviously we would pull them right into that little fish pond. And that's what net force is. So when I teach this with my students, I start out with something like this. These are force diagrams. If I had a box that was being pulled with a force of 4 newtons, and for right now all you need to know is newtons is a measurement of force. It's the way we scientifically measure force. Like temperature is measured in degrees Fahrenheit or degrees Celsius. In the United States, our weight is measured in pounds. Our distance is measured in miles. Well, force is measured in newtons. And I tell my students it's important enough for right now. That's all you need to know. If this box is being pulled with a force of 4 newtons to the right, the net force is 4 newtons to the right. But then you get into something like number 2, where you actually have 2 forces being pushed on an object, 8 newtons to the left, 4 newtons to the right. And so obviously 8 is bigger than 4, so the 8's going to win, and it's going to go to the left. What I have my students do is we actually turn these into integers. To the right is positive, to the left is negative. So this would be 4 plus negative 8, which means your answer is negative 4, which means you're going to have a 4 Newton force to the left. This one is going to cancel out because you have, to the right you have plus 3, to the left you have negative 3. 3 minus 3 is 0. We also say that up is very positive and down is very negative. So we turn them into integers, and every chance we get, we try to turn it into positive and negative numbers, because that way they can use the calculator and they don't have to do it in their heads. Now, problems like this are not a big deal because these are pretty numbers. And in my class we have pretty number days and we have ugly number days. On pretty number days we do math that you can do in your head. In Arizona, at least currently, we're not allowed to use any calculators on high-stakes tests, and that's all the way up through high school. That's unfortunate, but it's the reality. I've written those questions on those tests, though, and I can tell you that all the test questions are pretty numbers. It's 360 divided by 3. It's 2,400 divided by 6 or 60 or something like that. They're pretty numbers. We also have ugly number day because I want the students to be able to use the tool. On ugly number day, the numbers are, you guessed it, ugly. Instead of 360 divided by 6, it might be 359.72 divided by 5.631, something like that, so that they have to use the tool and they can get used to using it because they have to know how to use it. If they don't learn when they're young, they're going to be in a world of hurt when they get to high school or college and see it for the first time. Plus, the Casio calculators are so intuitive. If you get those, like I had a set that I got into the hands of 5th graders a number of years ago. I have those kids again this year, and they're really good at it. They have no problem. But you know what? The kids who've never seen those calculators before, the Casios are doing just fine with them too. So get it in their hands and get them working with it. Let's do some more forces. We talk about net forces in real life. So you've got the race car driver. He's got a force of 10 newtons to the right, and his little parachute is dragging, kind of slowing him down, 7 newtons to the left. What's the net force on the car? Plus 10 plus negative 7 gives us positive 3, so 3 newtons to the right. Balanced or unbalanced, in other words, is the sum 0 or is it not 0? In this case, it is not 0. It's unbalanced. Let's do another example. A dog is pulling with a force of 30 newtons to the right, and the boy is pulling back with a force of 18 newtons. What is the net force on them, and is the force balanced or unbalanced? Well, we can tell that it's unbalanced because they don't equal. 30 to the right plus negative 18 to the left tells me that the dog's going to win, and he's going to win by 12 newtons. There's a new movie coming out this summer or this winter. I've only seen the trailer for it, and there's it's called Frozen, and there's a snowman who loses his nose. It goes out onto the ice, and he tries to go and get it, and a moose tries to get it also, and the moose is going to eat it. And so the snowman's trying to get it before the moose gets it, and there's very little friction, and it's very interesting to see them try to move on a surface with very little friction. Again, a very good example of a real-world problem with friction and forces. All right, so last thing I want to talk about is just Newton's first law of motion, and this is one of my favorite ones. It says a body in motion tends to stay in motion in a straight line at a constant speed. And that's a thing that a lot of people somehow neglect or forget, that for Newton's first law of motion, it's got to be in a straight line and at a constant speed. Body at rest tends to stay at rest unless acted on by an outside force. We've all heard that before. I actually have my students mimic it with their bodies as if they're in a car. So they sit, facing forward. And how does your body respond when your brother's driving and he peels away from the curb? What does your body do when you turn right? What does it do when you turn left? What does it do when you stop? Once they get all that down, what I like to do is I like to give them a helium balloon and have them take it and hold it in the car. Not to suck the helium, but because that's not a good idea. Hold it in the car, just free in the air, and see what happens. I always can tell right away who did their homework and who didn't, because when a car starts and you're holding a helium balloon, the balloon actually moves forward when your body moves backward. It does the complete opposite of what your body does. And scientifically, that's because air has is more dense than the balloon, and so the air moves backward, which pushes the balloon forward when you take off. So that's a very interesting concept. So now my question is, do you have any questions for me? Does anyone have any questions? I'm really sorry about the sound. Now that we've done it, I seem to remember last time I had a problem with the sound as well, and I have to figure out how to better address that. I do apologize for that, but any questions? Terry, did you get all of our questions taken care of?
Yes, hold on a second. I don't have any other questions coming up.
Okay. Well, if there's no questions, I think that, one of my policies is start on time, end early, so I guess we'll end here. If you have any questions, you can certainly get a hold of Cassio or me or Terry, and we'd be happy to answer them.